Hi, good morning, everyone. Welcome back to Applied Thermodynamics. Last week, we talked about a single stage compressor cycle with and without clearance. On your right hand side, this one is without clearance. I would say this is, in other words, I can say this is ideal. This is with clearance. So what is clearance means there is some air trap inside the cylinder, the stroke. So some of the air trap it when it go back to the piston go back to the original place, the air expand, so it takes some of the space of the cylinder. So therefore, 3 to 4 rather than straight line is a bit curve, follow slightly to polytropic expansion. Well, so and we also learn about the minimum work in the compressor. So the ideally is we try to have a minimum work from 1 to 2. There are three-way option. So 1 to 2 double dot, this is 2 double dot, is isothermal if you look at this properly. So what that means is your compression, the pressure increase, but the temperature is exactly the same as T1. So this is T1 equals to T2. Well, this is ideally, but the thing that you can try to achieve is polytropic, which is close to PVN equals to N. Your N, if close to 1, then you are able to minimize the work. And the largest, the more work that then the workload of the compressor will be adiabatic compressor. So you might wondering what is the difference between the polytropic and adiabatic. I think we explained last class before. So for polytropic, you still have some entropy, but adiabatic, you don't have any heat transfer. So anyway, you can go back to the previous lecture to have a look further. But the problem is to achieve isothermal is quite difficult in a single stage. And your pressure is, the maximum pressure is roughly about 15, definitely not reach more than 100 bar, definitely not. But what if you need a higher pressure for, like, for example, an oil and gas plant, a power plant? What should you do with it? We can then introduce multistage. Okay, so multistage, the main advantages is to be able to install a cooler. I think it's somewhere here. Install an intercooler. I'm not really confirmed, but I think it's somewhere here, intercooler. And then it will cool down the temperature of the air, the compressed air, before sent to the next compression. So the good thing about this is you can condense the vapor, the moisture from the air from the first compression. So and before sent to the second stage. The good thing is reduce the risk of corrosion. The second one is when you reduce the temperature, so you also reduce the work in the compressor. And you can save a lot of energy from that. Besides of you able to achieve much higher pressure compared to single compressor. Well, if you look at the right hand side, it's multi-stage diaphragm air compressor. This one is this compressor is 3-stage compressor. Well, if you look at the second, this one is single stage compressor. The single stage only able to achieve 15 bar, whereas for the 3 stages, it able to reach up to 500 bar. All right. So anyway, it still depends on what type of gas you are dealing with. Yeah. So normally the multi-stage compressor are arranged in series. In series means after from this one, and then you send it here, and then continue send to another one. So the air after the compression in the first cylinder before enter to the next cylinder cool at constant pressure by passing through an intercooler. So the intercooler is work like a heat exchanger. The air cooled by either air or water. So it depends on what type of heat exchanger you're doing before passing to the next high pressure cylinder. So let's have a look on this diagram, the 2-stage air compressor. So the first one is the intake, all right? The fourth one is the inlet valve for the air. Okay, we have two here because we have two compressor. Number 2 is the intermediate chamber with cooler, the intercooler, right? The 3 is the pressure chamber to deliver out of the pressure gas. Number 5 is the pressure valve. You compress and then you deliver the pressure, the compressed air out from the pressure valve. Number 6 is the idling system, is to I think is to control the intercooler. Not sure about this. Number 7 is the control air. Okay, so in the first stage, the inlet air is compressed to approximately 5 bar, then cool in an intermediate chamber. In the second stage, is then compressed to the vehicle final or cut-off pressure. In this example is 12.5 bar. So can you imagine? So the first one is the cool air go to the first stage and then it's compressed. When you compress the air, it can reach 5 bar. But after you cooling the air and then you do the second compression, you're able to reach 12.5 bar. Can you see how amazing is that? So the air effectively cool, and if cooling is perfect, the temperature of the air is to return to the initial temperature. What does that mean? Is, so the air from the first stage is from T4, okay, and then to T1, and then go to the T2, right? So in this part, I would say, let me draw another picture for you. Then you will be, let me draw the, sorry about my poor drawing. The entropy, if you draw like this, for this stage, right? So, okay. So for T1 to T2, when you compress it, the temperature increase, the entropy increase, because this is polytropic, this is not adiabatic. So, and then we cool down 2 to 3, we cool down here. Right, do you remember? We try to 1 to 2, we compress it, and then we cool down the air, okay, to the temperature same as the T1. This is the isothermal, the perfect cooling. So first 1 to 2, 2 to 3, 3 to 4, okay? We are not looking at the 4 first. If, because tray 2 to 3 is compressed, and then you deliver the gas out. So the T4 definitely much higher. Okay? So the T2 is after you, okay? So later I will explain the whole curve for you. But at least I would like you to know that what is that mean is perfect intercooling is 1 to 2 is ice polytropic compression. After that, we have the intercooler. So the temperature reduced to T3. And then is in this part, T3 equals to T1. This is perfect intercooler. Right, okay? So what about the non-perfect intercooler? So let me try another color, maybe orange. Oh yeah. Okay. Try one more time. Okay. Okay, the orange. So if you are not able to have a perfect intercooler, your T3 will be slightly higher than T1. Yeah, this is the imperfect intercooling. So your temperature will be much higher than the T1. Is that okay? Are you okay so far? I think it's quite simple from this part, yeah? Yes, so next. So after this, so let's have a look. So if your question might be, so when T3 is same with T1, remember, yeah, this is P over V. This is not T over, this is not T over S. So when in a perfect condition, the T3 should be equals to T1. But this is very hard to achieve. If you look properly, when you cool down the air, the volume will be smaller. And instead of here, right? Instead of here, you move from here, you are moving slightly, going in a little bit, and start the compression, the second stage, 5 to 6. Okay, so the shredded part is the one that use the energy that you save. You reduce the volume and then you do the compression, okay, and then you deliver the pressure 6 to 7, and then you back to the original pressure as the P5. So are you clear with it? So make sure you understand this concept first, don't be confused. So there are few assumptions for this two-stage compression. The first one is we ignore the effect of clearance and we assume that there is no pressure drop in the intercooler and the compression in both cylinder is polytropic. So in this diagram, this whole diagram, okay? And the suction and the FAD take place at constant pressure. We assume that there's no changes in the pressure. Is that okay? So adverse effect of a single stage compression. So high delivered temperature resulting from high compression ratio affects the replicant system. The higher the compression, the temperature increase, they might be overheat your compressor. So the cooling part actually can prolong your duration, your compression. The volumetric efficiency of a machine is considerably reduced at high pressure ratio. So how this happen? If you look at this volume efficiency, is induced volume where over the swept volume. So what is induced volume? If we look at the previous lecture, okay, this is the lecture, the previous lecture with clearance. We have a look on this. The induced volume, okay, is the amount of air that compressed in the compressor. Whereas for the swept volume is the total cylinder, of the whole cylinder. The induced is only the compressed air. We ignore the clearance. If you look at your previous lecture, so if you look at this properly, so the induced volume is VA minus VD. The swept volume is VA minus V, I would say VA minus VC. The C is the clearance. Quite obvious, right? Okay, let's go back to this this week lecture. So the volume of induced is VA minus VD. I mentioned to you. So the VA is the swept the if you look back to here, VA. What is VA? VA is VS plus VC. VS plus VC, correct? Minus VD. Why minus VD? Because VD is the expand clearance air. So your induced volume is Vs plus Vc minus Vd, because your Va is Vs plus Vc. Since the process, let me see if I'm able to. Since the process in the polytropic process, so we can use the P1V1 power of n equals to P2V2 power of n. So we play around with the equation. So our VD, we can use the VD, put it in here, okay? So we can plug in back to this equation, then we can have this equation. So remember, the volumetric efficiency is over swept volume, Vs. And if you try to simplify it, then you can have this equation. It seems like this volumetric efficiency is greatly affected by the pressure ratio. If the higher the pressure ratio, the lower the volume. So we try to reduce the pressure ratio P2 over P1. Okay, so the smaller on this, the better we are. So from equation, the previous equation, so the ratio of P2 over P1 increase, the volume metric efficiency decrease. So, and this also another problem is the higher the pressure, the size of the cylinder will be too large as well. So in order to overcome the difficulty, for example, instead of you want to make one compressor to achieve, let's say 20 bar, you might need to design a huge single stage compressor. Your cylinder, your cost might be higher. But if you make a smaller compressor, but you want a higher pressure, you're able to achieve it if you have an intercooling between them. This is the advantages that I mentioned to you. Yeah, you can reduce the energy and therefore you can reduce the cost of the compression. You can make the size of the compressor even smaller, although they are multi-stage. Compared to single stage, you want to deliver the same pressure as multi-stage. Multi-stage will be much smaller compared to single stage. For example, I would like to have a single stage compressor with 20 bar. The size for two cylinder compressor to deliver 20 bar will be much smaller. And I mentioned to you, when we try to cooling down, the volume of the air will cool down, and also we try to condense the humid in the air. So this reduces the corrosion risk into the compressor. And also, when you compress, when you're cooling down, the volume of the air will be reduced. If you look at this picture, right? So therefore, you save some of the amount of the shredded area energy. Okay, this is the some of the energy. So how does the intercooler look like? This is some of the an example diagram. So the intercooler is simply a heat exchanger. To remove the heat from the air, you can put the coolant as air, or you can put the coolant as water, or you can put the coolant as refrigerant. It's just up to the efficiency, what efficiency that you liked. So by using the intercooler, the saving of work input up to 20%. You can save 20%. So sometimes you might say, I can save 20%, but I need to use some money to install the intercooler, isn't it? Is that worth for that? Well, for long term, yes, you can save lots of amount, and you don't need to put too much maintenance. You can reduce the risk, reduce the maintenance on the compressor as well, because the intercooler can cool down and condense the water humid in the air. Okay, so let's have a look on this diagram. It might be have a clearer information to you. Yeah, as referred to figure 4, from if I want to try to compress P1 to P2, the FAD is VA minus VD. Okay, so if I want to compress P1 to P3, this is the amount of volume I need to use. The higher the pressure, the higher the lower the volumetric efficiency. So if you look at this, okay, it seems like the higher the pressure, hence a required FAT size cylinder will be increased due to the pressure ratio increase. Okay, so the more volumetric efficiency decrease. After passing one first cylinder of fluid is passing to, okay, another words means you can reduce the size and you can retrieve higher pressure. In order to reduce the work, ideal isothermal compressor is required. If the intercooling is complete, gas will enter second stage at same temperature as the gas expelled from first stage I mentioned to you. The saving work obtained by the intercooler is the shredded part that I mentioned to you. So I think, yes, I explained too fast just now, so I can repeat again. From stage 4 to 1, from a normal cycle contact, this is called low pressure. In this part, this is called intermediate pressure, and this part is called high pressure. 3 to 4, gas expelled at constant temperature, and the air is then cooled at the intermediate pressure, which causes a contraction in the volume. So the volume of the air shrink a bit and make the induced volume V8 to V5 smaller than the expelled volume, like V2 to V3. Can you see that? So if the cooling is complete, the gas will enter second stage at the same temperature from the first stage. That's what I mentioned to you. It is assumed that the deliver process from first stage and the induction process of the second stage are the same pressure. In other words, means after P1 and then it becomes PI. So the pressure before entering the hash P stage, the PI should be the same. That's what that means. And then after the second stage, it will go to become P2. Since the gas expel polytropic condition, the delivered temperature from second stage are the T1 here is, because this is polytropic compression, and T2 is polytropic compression as well. So therefore, we can use polytropic equation to have this equation A for these two. So the optimum saving obtained by choosing correct intermediate pressure by the total work of the compressor will be W1, the work done by the first stage, plus the second stage. So less mass induced per unit time is m dot, okay, because per time dot is the time. So VA minus MA minus MB, YMA minus MB. So let's have a look on the previous slide. No, I think this is MA equals to MB. Okay. So the indicated power for compressor with clearance volume, let's have a look. Okay, if you look at the previous slide, at the previous lecture, the mass delivered per unit time is MB minus MC, the induced volume, or equals to MA minus MD. And therefore, we have MA minus, I think this should be MD. Sorry for my mistake. Okay, so if you look at the indicated power from the previous slide, it's this equation, okay, right? So this is definitely MA minus MD, okay. As referred to the equation 7 and figure 5, so the mass, the work for stage 1 is m dot equals to R T2 minus T1, and the work is T5, T6 minus T5. And since in this stage are polytropic, we can use polytropic, and we try to find the T6 and we plug it into the equation B, and T2 we try to plug in the equation B as well, we can get equation C. Okay, if the intercooler return to the air to the original temperature, like I mentioned to you, if the intercooler is doing well, so the T3 or the T5 after the intercooler, the T5 should be equals to T1. So therefore, the T5 here, I can write, if you look properly, this one become T1. And therefore, I can say this is also equals to this is the equation D. Okay, look properly, they are the same. Okay, for a minimum value of work, and in order to get relationship between PI, the intermediate pressure P1 and P2, we are differentiate with respect to PM and equals to 0. So we try to differentiate this work with PI. We can get this equation, and then equating to the 0 reveal that for minimum of work. So try to simplify it. Before that, we know that this is isothermal. So when we try to simplify this equation, we get equation number E. And we further simplify it, we know that Pi over P1 equals to P2 over Pi. And therefore, another words means I can actually, if ideally we can cool down the intercooler temperature T5 equals to T1, we can directly try to use this equation. If you have the PI or you have the P1 temperature, you plug it in, you can have your total work of the system if your intercooling is perfect condition. Okay? In terms of overall pressure ratio, we use the same equation E. So this is our equation E. We try to simplify it. Okay? And then, therefore, the total minimum work, we can try to use and play around with the E equation. Okay? And then we can replace Pi over P1, okay, into this one. Plug it in. Okay, we can also try to, if you don't have the intermediate pressure, it's quite hard to find it. You can also use P2 over P1 to find the total minimum work. Okay, so if your intercooling is perfect, let's say you have 10 stages, you can just times 10 to get the work, the minimum work. Also, the pressure ratio will be 1 over the Z. Depends on how many stages you are. I think that's it. Not that difficult to understand. It's just too many label on it. You can try to go back to have a look on that. It's just my mistake on this part. This is you can refer back to your previous lecture. So how come MA minus MD is the gas induced volume? A mass. So this is MA minus MD, not MA minus MB. Yeah. So thank you everyone. I will give some tutorial for you. Next week is Hari Raya. So I wish everyone happy holiday and Selamat Hari Raya. I apologize if anything mistake from me. And I hope you have a peaceful and wonderful holiday. Stay safe, everyone.